Good morning, or probably good afternoon by the time this gets posted. So I wanted to, here, don't look at that quite yet. This is where we stopped. In one of the classes, I was color coding this as polar versus non-polar. Now we did label them in all the classes, but here's just highlighted. And then also, if you see in red, this shows an example of a molecule that would fall into that shape. And I think there's just a couple that we didn't get examples for. Okay. Now on the next 2 pages, so starting here and below, there are some molecules, and then you're supposed to tell me, is the bond polar? And then are the polar bonds that are in that molecule equivalent? So what I mean by this is, like, if I had C, Cl, Cl, F, F, those are all polar bonds, but they're not equivalent polar bonds, because the difference in electronegativity between carbon and fluorine is, let's see, 1.5, whereas between carbon and chlorine, it's only about 0.5. Okay, so those are polar bonds, yes. So here's the questions we're answering. Polar bonds, yes, this has polar bonds. Are they equivalent? No. So even though they're in a tetrahedral shape, the molecule itself would be polar, because those polar bonds are not equivalent, so they can't cancel out. Okay, so that's how you're going to go through this. So pause the video for a second and do these practice problems just to make sure you're feeling comfortable with this concept of polar versus non-polar. And then I'm just going to show you the answers for, a couple seconds. You can pause the video and check your answers. So pause now and work this table and the next table. Okay, so here are the answers. And then for the next one, I ran through these relatively quickly, so if anybody notices errors, feel free to flag it in the comments. Okay. All right, so moving on today, like I said, this is a very different topic. This is called hybridization, and it deals with, we have to know the shape of the molecule. We have to know the Lewis structure, and then we have to also know the shape. But it is to help us understand what happens to the orbitals when we form a bond. Okay, so we're going to start with CH4, this molecule down here. And we want to first look at what do the orbitals look like for carbon before it's bonded to anything. So if you remember, the valence shell of carbon has 2 electrons in the s orbital and 2 electrons in the p orbital. In 2 of the p orbitals. And then in the hydrogen, there's just that 1 s electron. Okay? Now, if you remember the shapes, the s orbitals are a sphere, and the p orbitals, there's 3 of them, and they're kind of these dumbbell shapes. And then there's one going in and out of the page. So I'll just draw that like a dashed thing. So they're all perpendicular to each other. Well, if I bring hydrogens along, so here's a picture of those s orbitals. If I try to bring hydrogens along and bond them with the p orbitals the way they are right now, it doesn't match up with the shape that we know CH4 looks like. If you remember, CH4 is tetrahedral. So it's kind of pointless for me to even try to draw it now that I think about it, because it's 2-dimensional. So let's see, do I have a picture? Yes, there we go. So we know that it's a 3-dimensional shape and that the bond angles are 109.5. The existing bond angles for the p orbitals, though, are 90 degrees. So that must not be what's going on. These standard s and p orbitals must not be an accurate representation of what's going on in the carbon. Okay, there must be more to the story. So we're saying this is what we thought carbon would look like, but once it's in a bond, that doesn't match up with what we actually see. This is what we actually see. Okay, so the model that we use to explain this is called hybridization. Okay, so it is a model. It is not, how do I say this? none of these things are perfectly true or perfectly representative of what's going on in an atom. But in this case, it's a very good representation and allows us to predict a lot of things. Okay, so the idea of hybridization is that the s and p orbitals in carbon kind of get smushed together, and then 4 new orbitals are made. This is once it's in the molecule, so this would be atomic orbitals for carbon by itself, and then this would be carbon in the molecule CH4. Okay, so we take all 4 of these orbitals, the 1s and the 1, 2, 3, 4 p's. We make 4 new orbitals, 1, 2, 3, 4. So the number of orbitals that we start with is going to equal the number of orbitals that we end with. The difference is the ones that we end with are going to be equal in energy, and they're also going to have the same shape. So the same shape as each other. In fact, they will be a mixture of the S-shape orbitals and the P-shape orbitals. Let me see if I have a picture here next. There we go. This is the one I was looking for. So here's what we start with. Carbon by itself, an S that's a sphere, 3 Ps that are all 90 degrees apart. And what we end with is 4 different orbitals that have a little bit of that dumbbell shape, but they also have, so we still got the 2 lobes, but if you see one of the lobes is like rounder than the other, so that's the spherical portion that is contributed from the s orbital. So they're kind of like these offset dumbbells, if I zoom in a little bit. And the thing that makes a whole lot of sense and matches with what we see in the molecule CH4 is that they are all 109.5 degrees apart. Okay, so we start with 4 orbitals, we end with 4 orbitals, and the 4 orbitals we end with, their shape corresponds to the shape of the molecule itself. The other thing that's a really important note is that the number of orbitals, let me go back to this point. The number of orbitals that we start with and that we end with is also going to be equal to the number of electron regions. Okay, so in CH4, we had 4 electron regions. That means we need to use 4 orbitals, and we're going to make 4 orbitals. Okay, which 4 orbitals do we use? Well, all that carbon really has in the valence shell is 1 s and 3 p's. So that's where those 4 orbitals come from. Okay, and then we make these new 4 orbitals. So those 3 numbers all need to match up. This is like a key thing. You're going to look for how many electron groups there are. You're going to take that many orbitals from the starting atom and make that many new orbitals. Now, the name of these new orbitals, it's not S and it's not P. What it is a combination of however many S's and P's you mix together in order to get these. So if we look at, let's look at this picture to look at this. If we look at these orbitals, we said that their shape is kind of a mixture of S and P. Well, the way it is it's 1 part S and 3 parts P. Think about if I took all of these orbitals and I dumped them into a container. Okay, so we've got 4 orbitals, an S, a P, and a P, and we're going to mix them up. Okay, so shake up the container, and then we're going to divvy that container back out into 4 new orbitals. So think of them as like smaller cups, right? Well, from those original orbitals, a quarter, and I'll do this in the same colors, gray, a quarter of that new orbital is s, right? Because there was one s orbital and it got mixed in with 3 p's. So now a quarter of that s is divvied back out. And then 3 parts, 1, 2, 3 parts p, so 1, 2, 3 parts p are part of that new orbital. Think of it as like we're dividing every s orbital into 4 parts, and we're giving 1 part to each new orbital. Okay, so that's why it's a quarter s. Then we're doing the same thing with each of the p's. We're dividing it into 4 parts, and we're giving 1 part to each orbital. And if we do that with all 3 of the p's, that means that each orbital has turned into 1/4 of an s orbital and 3/4 of a p. If this is like sounds ridiculous to you, because how in the world can we mix up orbitals and divide them back out? No, that's not really what's going on, but the thing that results when carbon bonds with hydrogen looks exactly like this. It has the shape, it has the energy associated with a quarter s orbital and 3/4 part p orbital. So I'll think of a good analogy in a second, I'm sure. So we'll come back to this. The way we label these is we say however many parts there are. So there's 4 parts total because we started with 4 orbitals. We label that with a superscript. So it would be like S, there's only 1 part S contributed because we only mixed in 1 S orbital. And then there's 3 parts P contributed because we mixed in 3 P orbitals. Okay, we don't write the 1, so I'm just going to erase that here. We just call it an sp3 orbital. And what that means is that it is an orbital that came from the mixing of 1s and 1, 2, 3 p's. Okay, so that's how we label these. So obviously we're going to do more examples of these. We're going to look at ones that are something other than just sp3s. But the key point that you're going to keep coming back to, figuring out where to write this. The key point that you are going to keep coming back to is first, you're going to determine the number of electron regions, which you're experienced doing this now. We do it all the time. We count them up, either a double bond, a single bond, a triple bond, a lone pair of electrons. Those each count as 1 electron region. Then you're going to start with that same number. So same number of what we call atomic orbitals. So from the atom itself. So this is going to be S, however many we need the same number. S, P if we need them, and then even D's if we also need them, okay? Keep in mind, though, you only have 1 S available. This is stuff from chapter 9. So if this stuff is seeming like, what is she talking about? 3 P's? How do I know that? Go back to chapter 9 and review that, okay? And then in the D's, we actually have up to 5 available. So in theory, we could have an sp3d5 orbital. That's not actually going to happen. The highest values we're going to see are sp3d2. But you could, in theory, go up to 5 because you have 5 d orbitals available. Okay, so we start with the number of atomic orbitals that matches up with the electron regions, and then we make that same number of, we call them hybridized orbitals. Okay, that's the key point. And the way that we label the hybridized orbitals is the orbital, and then however many of those orbitals we mixed in, the orbital, however many we mixed in, the orbital, however many we mixed in, okay? And the number of how many we mixed in, maybe I should use a different designation here than just, because it's not the same number as what you found in 1 and 2. It could be, well, let's just do examples. I think it'll be easier. But this is like, you're going to name this like S if there's 1 S mixed in, P3 if there's 3 P's mixed in. Maybe it would be like SP2 if you only mixed in 1 S and 2 P's. Okay? It'll make more sense when we do some practice problems. All right, so NH3. We've done this Lewis structure a million times. I'm going to go ahead and draw that in. Okay, the atomic orbitals we had for the nitrogen. This is specifically for the nitrogen. We don't care about the peripheral atoms, just like we talked about before when we were looking at shape. So originally we had S and P, and nitrogen had 5 valence electrons. Okay, and we want to start step number 1. We're going to count the number of electron regions. So 1, 2, 3, 4. Sorry about that. Obviously, there's someone outside. I have 2 very defensive dogs. Okay. They feel like they need to bark at absolutely anything, I guess. Okay. So the hybridized orbital diagram also needs 4. Okay? Because there's 4 regions. 4 here. I'm going to use 4 here. And I'm going to make 4 there. So I use all 4 of these. And I make 4 new orbitals. Each one being 1 part S and 3 parts P. Now, each orbital is called an sp3 orbital. So there's 4 of them, but they're each called sp3. And then we can also go ahead and put those valence electrons back in. We may or may not get to this in a lot of detail, probably when we see a little bit more complicated examples, but we can put those 5 valence electrons back in. And what's interesting here that you can see kind of right away is that, let me change the color coding here, is that this lone pair on the nitrogen is represented by this orbital because there's 2 electrons in it. And then each of these bonds is represented by the, leave those yellow actually, is represented by each of these half-filled orbitals. Because then what happens is that the hydrogen brings its 1 electron in and overlaps with that orbital. Now, I just said an interesting word. I said it overlaps with that orbital. Let's go back and look at this picture here. So one of these electrons in this carbon came from the carbon, and one of them came from the hydrogen. And the carbon had its orbital with that 1 electron in it. The hydrogen had its orbital with the 1 electron in it. And then the 2 orbitals like physically overlap. And that's what creates the bond. That type of bond where the orbitals, these half-filled orbitals, are physically overlapping, we call that a sigma bond. It's just a designation for this type of bond because we're going to see a different type of bond in a second. But when you have this direct overlap of orbitals, that's called a sigma bond. Okay? All right. We're going to look at a picture or a visualization of these. These aren't super interesting when you're talking about simple molecules like this, but still. So this is NH3, and we can look at the sp3 orbital that's on nitrogen. That is one of the sp3 orbitals that we saw in that picture. It's half filled, so it's not the one with the lone pair. And you can tell that it's the one that's with the bond because it's right next to that hydrogen that it's going to bond with. In fact, I can turn on the bond I can turn on the orbital for hydrogen and show you how that hydrogen overlaps with the nitrogen. Okay, that's the sigma bond that I was talking about. So this is an orbital on nitrogen, and it overlaps directly with that hydrogen's orbital, and then that creates the sigma bond. We can also look at, let's see, 1, 2, 3. We can also look at the nitrogen lone pair. That would be the one that has the 2 electrons in it. And obviously they're like on the top there. There's no bond. There's no atom that it's bonding with. Okay, so you can come to, there's links throughout the notes. I probably won't open up every single one, but you can come and look at the orbitals themselves. And remember, orbitals are just a place where the electrons are going to be. Like, this is where they are likely to be around the molecule. Okay, so we're going to use this chart again, and we're going to connect the fact that we've gone through this chart a number of times and said everything in this first row, that has 2 electron groups. Everything in the second row here, that has 3 electron groups, 4 electron groups, 5 electron groups, 6 electron groups. And we're going to talk about what the hybridization is dependent on the number of groups, because it's actually the same for each type in a given row. So like everything in this row, because we've done 2 of these so far, will be sp3. How do I know that? Let's remind ourselves what the base orbitals look like. I have to move this over so I can include the D's. S, 3 P's, and 5 D's. Okay, that's the orbitals you have to play with. I could never say something is sp4 because I don't have 4 p orbitals. I only have 3. So I'm going to take as many orbitals as I need so that I can match them up with this number over here. Okay? So this is S, this is P, and this is D. Okay, I'm going to take only as many as I need, not more than that either. All right, so number 2, row 2, electron groups, 2 electron groups, this first one here. I should be highlighting instead of just saying here because I can't point when we're in a video. Okay, this here. 2 electron groups means I need 2 orbitals. Remember, the numbers should all match. 2 electron groups means I need 2 orbitals, which means I will make 2 hybridized orbitals using these 2. What is the name of them? These 2 new orbitals? They're called sp. Why? Because I used 1 s and 1 p. Okay? I don't actually have to draw them out. I just want to emphasize the fact that there's 2 of them. Okay? So maybe when we finish, I'll go back and erase the actual lines that I've drawn as reminders. But the label of these orbitals is sp. That's an sp. This is an sp. Okay? What we're basically saying is that each of these orbitals is like a half s and a half p. Because I put them in a big pot. I put the s in and I put the p in. And then I mixed it up, and then I poured it out into 2 new pots, new orbitals. And what I would get then is a half s and a half p in each one of them. So I would say this is S and P, this is S and P. Okay? I'll do this analogy on the next one as well. Okay, so let's erase some of this so that we're not overlapping. So for the next one, for 3 electron groups, okay? 3 electron groups, so either one of these shapes, but 3 electron groups, I'm going to take 3 orbitals, 1 s and 2 p's. I always have to start with the s's because I always have to start with the lowest energy possibility. So 1 s and 2 p's, and I make 1, 2, 3 new orbitals, and I call them sp2 orbitals. This is an sp2, that's an sp2, this is an sp2. Okay, what does sp2 mean? It means I took one s and two p's. I put them in a bucket, S, P, P. I mixed it up and I poured it out into 3 new containers, each having 1 part S and 2 parts P. 1 part S and 2 parts P. 1 part S and 2 parts P. Okay, so each one of these now is labeled 1 part S, 2 parts P. I don't write the 1 in there, but just to make a point, that's what those superscripts mean, is how many orbitals of that type did you mix together. Okay, now for 4 groups. This is one we've seen already. Okay, 4 groups. So all of these guys. So I'm going to grab an S, and I need 4, so I grab all 3 of those P's now. And now I make 1, 2, 3, 4 orbitals. I call them sp3 orbitals, and there's 4 of them. Okay, now we're getting a little bit more complicated here with 5 and 6 groups. So 5 groups, I need to take 5 orbitals. So an S, 1, 2, 3 P's, so I've got 4, and then I'm going to grab a D as well. So I take those 5, I mix them up, and I make 1, 2, 3, 4, 5 new orbitals, and I call them S, P3, D, because I used 1 S, 3 P's, and 1 D. Just to emphasize the point crazy a lot, the number of electron groups is the number of orbitals I grab, and that's the number of orbitals I make. Okay, last one. 6 groups, 6 orbitals. 1, 2, 3, 4, 5, 6. I need to get 2 d orbitals in this case because I need it to match the number of electron groups. 1, 2, 3, 4, 5, 6. And each one of those would be labeled S, P3, D2. Okay, this is summarized in the next table. The labels, at least, are summarized with the number of electron groups. Okay, and then you'll see it matches up with the shape as well here because there's a inherent connection between the number of groups, the electron shape, the electron geometry, the hybridization, and then what it physically looks like. So all of those things are connected. All right, we're going to try another one, and this one is going to start introducing us into what happens when we have a double bond, okay? So the Lewis structure of this one, you can go ahead and draw it if you want to pause now and do that. So this is what the Lewis structure looks like. Without even drawing the orbitals, because you don't necessarily have to draw them. I'm going to in a second, but just to point this out, I'm just going to count up the number of groups. 1, 2, 3, surrounding the central atom. And so I know I need an S, but I need 3 total. So I'm going to use an S and 2 P's. That is the hybridization on the carbon. That is what the orbitals will look like. It will be sp2 hybridized is the way we say that. Okay, so the carbon atom originally looked like this, had 4 valence electrons. The new one actually only has 3 orbitals. And what else is interesting is that, remember this p orbital over here that we didn't do anything with? Like, we took these, we hybridized them, and we made sp2 orbitals. We actually have a p orbital left behind, okay? One of the unhybridized orbitals, like originals. Original, okay? So when I take these 4 electrons, I'm actually going to put 1 in each of them. And I'm going to show you real quickly, or real soon, what happens with that original orbital that didn't get hybridized. Okay? So I'm going to open up this picture here. This isn't exactly the one that I wanted. So I need you to pretend that this top carbon, I can't point at them. That's difficult. You know what? Maybe just to not confuse the point, maybe I'll just draw it instead. In fact, do I have a picture? Ooh, I think I do. Yep. Okay. So this depiction of the orbitals is shown down here again, just to emphasize the point. So you have it drawn for you as well as what I drew. And then we have the electrons in there. So the 3 in the sp2s and the 1 in the p. And what they actually do is they form 2 types of bonds, okay? We're going to have, I'm trying to think of how to handle this all at once, okay? So to start, ignore these crazy looking things up here, okay? Just look at the purple ones right now. So that's the carbon. So like redrawing the Lewis structure, it's drawn like this. Okay, so here's the carbon in the middle. There we go. Here's the carbon in the middle. There's the hydrogens, and here's the oxygen. Okay, there is an orbital, an sp2 orbital, because remember we said that's the type of orbital we're using, sp2 orbitals, that's forming an overlapping bond with the hydrogens, okay? 1 electron from the carbon, 1 electron from the hydrogen. Here, as well as here, that's a sigma bond between the carbon and the hydrogen. And then there's also a sigma bond between the carbon and the oxygen. So this color isn't great. You just use a regular pen. So this bond here is the overlap of an orbital from carbon and an orbital from oxygen, and they're forming, as it's labeled here, 1 sigma bond, okay? When orbitals overlap directly, that's when you get a sigma bond. And that is always, it's kind of like our most basic type of bond. Anytime you have a bond, that's where we're starting with, is 2 orbitals overlapping, sharing electrons. Now, the reason I'm emphasizing that so much is because now we're going to talk about the second bond that exists between carbon and oxygen. So we looked at one of the bonds, right? Now we need to look at the other bond. Where did that other bond come in? Well, the space right between the carbon and the oxygen is already taken up. We cannot have any more physical space there. We can't throw another bond right in here because there's already a bond in there. So the second of those bonds, excuse me, the second of those bonds comes from this unhybridized p orbital up here. So one of these guys formed a bond with the hydrogen by overlapping. One of them formed a bond with the hydrogen by overlapping. And one of them formed a bond with the oxygen by overlapping. We have another carbon-oxygen bond, and that's what we're going to use this unhybridized p orbital for. Okay, so let me clean up this picture a little bit so that we can start fresh. So we talked about the sigma bonds, and now we need to talk about that pi bond. So I just gave it away. When you use an unhybridized p orbital, we call that a pi bond. Okay, so this is representing the unhybridized p orbital. There also happens to be one on oxygen. You don't need to worry about that right now, why that is. But there's an unhybridized p orbital on the carbon and an unhybridized p orbital on the oxygen. And they interact, it's not really an exact overlap, but they interact above and below that sigma bond. Those two regions that I just colored in, that is one bond. Okay, that is one bond, even though it happens in two different spaces. Anytime you use two orbitals and interact them or overlap them, that just makes one bond. So the sigma bond is the direct overlap here of hybridized orbitals. The pi bond is the interaction of unhybridized p orbitals, and it occurs above and below that sigma bond. So it's not in the exact same physical space. That was a lot, I understand. If you're freaking out a little bit right now, we're going to spend Wednesday reviewing this stuff, because what's nice about these chapters is that they all build on each other. So I could literally on Wednesday give you one molecule and ask you to tell me everything about it that we learned in chapter 10 and 11. So it's not like we need to go back and review chapter 10 separately. So on Wednesday, we're going to spend the whole time reviewing by giving you a molecule and talking about the stuff we talked about before, like what is the Lewis structure, electron geometry, molecular geometry, is it polar, what are the angles, but then we're also going to talk about the hybridization. So it's not like this stuff is just today. We're going to do it on Wednesday as well. Okay. All right. Let's keep looking at examples for the rest of today's stuff, though. All right. So we'll come back to this. This is basically just reiterating. In fact, no, we won't come back to it. I'll just emphasize it again. So this is reiterating the idea that if you have two overlapping orbitals that overlap directly, that's a sigma bond. If you have them interacting in these two regions, like above and below where a sigma bond would be, that's a pi bond. Okay, so just kind of differentiating between sigma and pi a little bit more clearly. All right. I'm thinking. Before we do this one, I want to look at the one that I clicked on up here. This one. So this link here, that actually brought up this molecule. And I want to actually look at that now because it might be a little bit easier to understand. So this is really similar to this guy because instead of an oxygen being there, there's just like another carbon and hydrogen there. Okay, so I want to be able to look at the orbitals with you now and hopefully have you see what that pi and sigma bond look like. Okay, so we're going to focus in on one of the atoms, one of the carbons. In fact, what I'm going to do, remember when I opened it up earlier, I oriented it so it was up and down. So I'm going to position the molecule like this, and we're going to look at this carbon. Okay, we're going to look at the sigma bonds it forms with hydrogen. We're going to look at the sigma bond that it forms with the other carbon. And then we're going to look at the pi bond that's like above and below that sigma bond, or I guess it would be left and right in this orientation. That's the pi bond, or the second of the double bond. So just to be clear, in this particular molecule, I'm going to highlight the sigma bonds in pink, okay? So that's a sigma bond. This is a sigma bond. One of those is a sigma bond. Those are sigma bonds. And then the pi bond is the second of the double bond. Okay, so you can only ever have one sigma bond in a given region, and any additional bonds, a second or a third bond, would have to be pi bonds, or unhybridized p orbitals that interact either above and below or left and right, but not immediately in the space between the two atoms. Okay, so let's try to look at that depiction here. Okay, so I'm going to turn this way. We're going to look at that bottom carbon. So the first thing I want to show you is an sp2 orbital. So what you're looking at is the region of space where the electron that is going to bond with the other carbon's electron, where that electron is. It's somewhere in that bubble, that blob, okay? So it will then overlap with the other carbon's sp2 orbital. Oh, that's not the one I want. This one. And when those overlap, that is a sigma bond. Okay? That is a sigma bond between an orbital on the carbon and an orbital on the other carbon. Okay, so that is one of the sigma bonds. Another one is the carbon and the hydrogen. Those orbitals overlapping, that is a sigma bond. And then the last one is this carbon and that hydrogen, and those overlapping, creating a sigma bond. Okay? Now the pi bond. So you'll notice when you look down this list that says hybrid orbitals, those are the ones at the top just say PZ. So I'm going to select PZ to twist it to the side so you can see it. That is the unhybridized p orbital. It is going to interact with the p orbital on the other atom, and when those interact, that is the pi bond. Okay, so I'm going to be able to draw on here. So this, the orange and yellow, that is the pi bond. I'm writing it twice so that you see that I'm talking about both space above and below, but that is one bond. The other bond is in here. It's that direct overlap between the orbitals here and there, and that is the sigma bond. Okay, so in the middle, sigma, and then above and below, pi. Okay? All right, we're going to do one more with a triple bond. And that is C2H2. Okay, so before I even look at hybridization and everything, I know this guy is going to be a sigma bond, meaning it's going to be a hybridized orbital that overlaps. One of these is going to be a sigma bond. This will be a sigma bond too. And then one of these will be a pi, and the other will be a pi as well. Okay? So let's talk about hybridization. We're only going to talk about it for one atom because it gets really confusing if you're trying to talk about it for a bunch at the same time. So for this carbon, there's two regions, right? One region, two region. So two regions, which means I need to use two orbitals to make two new atomic or hybridized orbitals. So I always take the S because it's the lowest energy one. And let's draw it up here. And I grab one of the P's because it's the next in energy. And so I make two new ones called sp orbitals. And remember, let me redraw this so I can get a little bit more space. One second. Okay. So going back to those orbitals that were on the original ones, I had S, P, 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 right? I used 2 of them to make the 2 sp orbitals. And then, don't forget, I have those leftover p orbitals that I didn't do anything with. Well, your sigma bond on this yellow carbon in particular, your sigma bonds are going to come from here and here, and the pi bonds are going to come from those p orbitals. Okay, the reason I haven't talked about this one is because that's on the other carbon and we haven't looked at that. So let's just erase it for now. Okay. All right, so let's look at the picture, the visualization of the orbitals. That is not the right one. It opened up the wrong. Let's see. Hang on one second. Fine. There we go. Okay. 2 carbons, 2 hydrogens. So first, let's look at the sigma bonds. So one that's coming from the carbon on the left overlaps with the carbon on the right. That's the sigma bond between the carbon and the carbon. I also have the sigma bond between the carbon and the hydrogen. And then I have 1 pi bond between the 2 carbons and another pi bond between the 2 carbons. Okay, so 3 bonds. 1 is a sigma in the middle, 1 is a pi like up and down, and then 1 is going to be left and right. So let me so that's 1 pi bond. Let me turn on the other one while we're looking at both. Okay, so it like encircles that bond area. I'm going to turn them off and on again. So sigma is here in the middle. Okay, pi bond is here. That is hard to see, isn't it? Let me turn off the sigma bond, okay? So the sigma bond is right in the middle where the bond is, where the bond length is. 1 pi bond is kind of above and below that sigma bond. You can do this as well, but so above and below that. And then the other one is going to appear front and back in the way we're looking at it, okay? So there's 1 sigma bond, and there's the second. Okay, kind of wacky. Okay, so this is a depiction of that that's maybe in some ways a little bit clearer. So you have, use black. Okay, so you have the sigma bond between the carbon and hydrogen. You have the sigma bond between the carbon and carbon. And then you have the pi bond between this carbon and that carbon. And then you also have one going kind of the in and out of the page direction. Okay, so that's what's represented here with the red, is they're showing there's one kind of up and down, and one that's like front and back. But remember, each of those 2 up and down, that's 1 pi bond, and then the front and back, that's another pi bond. Okay, so what kind of questions can I ask about this? That's always like the next thing. I'm not sure how long this has been yet. It feels like it's about the right amount of time, but let me just wrap it up with what kinds of questions could I ask you about this? Okay, this is a great one. Let's take just one question at a time. So write the hybridization next to each carbon. Okay, let's just start there. And then we'll do bond angles after that. So this is all dependent on number of regions. Okay, So in fact, we can do the bond angles at the same time because guess what? They also are dependent on the number of regions. So just as a refresher, 2 regions would be 180 degrees and it would be sp hybridized. 3 regions would be 120 degrees and it would be sp2 hybridized. 4 regions would be 109.5 and it would be sp3 hybridized. 5 regions, that's where we get the 120 and 90, and that would be sp3d. This is when we start to use the d orbitals. 6 regions is going to be 90 degrees, and it would be sp3d2. Okay, so leaving that there is kind of a hint, a reminder. Let's look at each of these carbons. Now, if this was an actual question on the test, I would have to like label one and say like this, and I would say, tell me the hybridization and bond angle for carbon 1. Okay, or I could say something like, tell me the hybridization for carbon 1, 2, and 3. That's probably the most I would expect, in a question like this. This one's like combining a lot of different things or just asking a lot of different questions. Okay, so the first carbon, going left to right, 1, 2, 3 groups. Okay, so the bond angle is 120 and the hybridization is sp2. Second one, so I'll erase the highlighting so that doesn't get confusing. Second one, 1, 2, 3. Oh, it's the same. 120 sp2. Okay, next one. Oh man, this is kind of boring now. 1, 2, 3. 120 sp2. Next, 1, 2, 3, 4. Okay, so 109.5 sp3. Next one, 1, 2. So 180 and sp. And then the last one, 1, 2, so 180 and sp. Okay? Just remember, everything from chapter 10 to chapter 11, they're all connected. Draw a good Lewis structure, predict molecular geometry, electron geometry, hybridization, bond angles, all of that stuff. It's all connected together. Oh, here's another interesting question. Okay, down here. How many sigma bonds are in the molecule and how many pi bonds are in the molecule? So let's highlight these. We'll do sigmas in yellow and pi bonds in pink. So anytime there's a bond, it's first a sigma bond. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 sigma bonds. Because that's the bond that's always going to happen anytime you have 2 atoms bonded together. If you have a double bond, that's where the second of those 2 bonds is where the pi bond comes into play. So pi bonds, 1, 2, 3, 4. So that would be a great question too. Indicate the number of sigma bonds and pi bonds. And maybe the answers would be like 12, 4, 4, 12, 16, 0. I don't know. Some other random thing. Okay. we'll do a couple of these. I'm obviously going to leave some for Wednesday. Not even a couple. Let's just do, let me pick and choose. So it's just hybridization. Oh, it's assuming we've already drawn a few of these. Okay, we'll just do a couple because we can do the ones we've drawn before. So we'll do SF4, SF6, and SO2. Okay. So SF4, if you go back and look at your notes, we decided it looked like this, with the lone pairs on all the fluorines. Drives me nuts to have to do that, but I don't want to confuse anybody. Yes, those lone pairs are there. I'm not going to get lazy and not draw them. Okay, so I look at the number of regions for hybridization. 1, 2, 3, 4, 5. So that number of orbitals is what I need. 1, 2, 3, 4, 5. That's it. That's how I determine the hybridization. Okay, SF6 was like this. Fluorines all around. All those lone pairs. Remember, we only care about the central atom when we're talking about shape and hybridization and all of that. 1, 2, 3, 4, 5, 6 regions. So I need 1, 2, 3, 4, 5, 6. SP3D2. Okay, last one. If I can get this one erased. It's probably good enough. SO2 looks like this. So 1, 2, 3 regions. So SP2. Okay, that's it. That was all you would have to do to determine hybridization. Okay, list of exam topics here. I think we kind of have hit most of them throughout this unit. Kind of some things that maybe might be a little bit rusty. I feel like we've done plenty on resonance. Maybe formal charge a little bit. Bond length and strength. Properties of ionic versus covalent. That was like at the very beginning. Otherwise, you know, a lot of that stuff has been encompassed in chapter 11. Okay, so on Wednesday, I will come in with, we might use these ones, but we'll come in with a number of molecules, and you're going to predict the hybridization as well as, you know, all of those other things, the shape and the angles and everything. Okay, feel free to leave comments. I'll try to check them today, this evening, tomorrow, and then we will meet back on Wednesday in class for practice review. Feel free to bring any questions. If you want to do the chapter 11 practice exam, that would be a great idea to do that and bring in questions. Do keep in mind the homework for chapter 11 is due tomorrow night. So that's the priority. But once you finish that, if you wanted to work on the practice exam, that would be good as well. Okay? Take care.